The last speaker of the symposium this year is a colleague of mine, Don DePaolo. Don has a very distinguished career. He is a geochemist by training. He went to Caltech and actually worked with Jerry Wasserberg, who was a graduate of Rutgers University a long time ago. Don has a lot of credentials. I don't want to go into them all, but for the last several years, the most important job he's had has been relevant to our conference today. He's been the Associate Lab Director, which is a very high position at the Lawrence Livermore National Laboratory, and his responsibility is the Director of Energy Sciences. And for those of you who are not familiar with national laboratories, they do not operate like universities. They have staff scientists, which are essentially tasked with, to work in teams in many cases, to solve large-scale problems. And so that is very much the role of Don, is to try to understand the best ways forward strategically for the laboratory in the nation, as he is essentially he's essentially hired by the Department of Energy for that job. So without any further ado, Don's going to talk about carbon management research agenda. Don.
Yes, thanks very much for the invitation, Paul. Very happy to be here and give you sort of an overview of some of the things that I think are important about the picture that we're trying to solve. The way I've got this talk set up, it's a little bit of one thing and a little bit of another. So the first part, I wanted to give you my view of where we stand with regard to carbon emissions and where we might be able to go with that. And I'm a geologist, and so I want to reference things to what the Earth normally does. And then we'll talk about how to get to where we want to go. And of course, all the speakers have been touching on this issue, and there's different ways to look at it. And I want to give you a particular way to look at it that I feel does something for me. We'll see whether you feel the same way. And then I want to finish up by talking a little bit about what's happening in the major research efforts funded by the Department of Energy that are addressing various aspects of sort of low carbon energy in one way or another. And part of the reason I wanted to do this is that in the end, and it's not clear why it's gotten to this stage, but it's partly maybe a response, something that Steve Chu helped it happen at the Department of Energy. Actually, there was Ray Orbach and some other people before that. Their research portfolio that the Department of Energy has right now actually makes quite a lot of sense. And you could argue about whether they should put more resources in certain areas than they are, but nevertheless, they're working on mostly what I think are the right things. So let's look at the carbon situation for a minute. And these are the latest numbers from the Global Carbon Project. So just this past year, we reached about 10 gigatons carbon per year, and this is just from fossil fuels and cement. The land use change part is down here. It's getting smaller. It was never, in my view, as important in any case because you can cut down trees and you can burn them, but they grow back. And as a matter of fact, that's a time scale of decades, and that one we don't have to worry about that much. Initially, that was a problem. Back here, that was a big part of what was going on. It's trivial now. And in fact, the latest IPCC report says that regrowth due to sort of CO2 fertilization has pretty much canceled out all of the land use change that happened out previously, and the total net change in the terrestrial biosphere has been about zero. Okay, so if you look at what's going to happen in the next few years, and this, so Jennifer had this reaching about 44 gigatons in 2050. GCP has it reaching it in 2020. So the prospects are not too good. Things are getting bad at a rapid rate with regard to emissions. Furthermore, this trend is not a good one either. Coal is now by far the most widely used carbon source, and it's growing very rapidly. You can see it here, and of course that's due to India and China. Cement, by the way, is down here. It's pretty substantial now, and it's growing also, but you can see that this is a much smaller effect than the others, And my view is that when you think about building materials, the scale of what you're going to be able to get is somewhere down here, you know, sort of in this neighborhood of what you produce in terms of CO2 from cement. So that's going to be a pretty small part of the overall picture. Okay, now this diagram, you know, is old. This is from the 2005 IPCC report, and this was one of the models that their scenarios that they run. And this basically, this line here was essentially the business as usual case, and they thought that was the worst case scenario. So that was in 2005, and they projected that in 2015 we'd be here, and that 2025 would be over here. Well, this is where we actually are now, and this is where that graph shows that we're going to be in 2020. So what used to be a pessimistic prediction of CO2 emissions is now looking like an optimistic one, and we've got a lot of work to do, and I think the point is that we need to get started pretty soon. In terms of global integrated emissions, again, the ultimate effect of carbon emissions is essentially proportional to the total amount emitted. It's not that sensitive to the amount of time over which you emit it. You know, and the difference between going this route or the route we're going now versus what we used to think might be possible is getting larger. Okay, and then finally, you know, and you've seen this in various forms probably if you've paid attention to this literature. This is the emission rate and as a function of time. This is the historical rate. This is the current IPCC worst case scenario that's taken out toward the end of the century. And this is sort of projections of where those might end up if you eventually got them turned around and headed back towards zero emissions. At this point, it seems to me that this one here, which represents about 1,600 gigatons carbon, would be a miraculous achievement, okay? And we might be somewhere between that and this. But you can see here that the next 100 years is going to be really critical. So again, the issue, in my view, is we need to get started, and we need to get started soon. And in terms of, you know, how long this stuff lasts, this is a figure that's also from the last IPCC report that follows on from the work of Archer and others. You know, over the next couple of 100 years, this is the part that goes into the atmosphere, this is the part that goes into the ocean, and the land biosphere is going to take up some. But my view is that after 100 years or so, the land biosphere is not going to be doing anything anymore. And then, you know, you're looking out first 200 years, then 2,000 years, and then 10,000 years. And, you know, if you actually pump 5,000 gigatons of carbon in the atmosphere, thousands of years from now, we will still be up in a range that the Earth hasn't seen for millions of years. So this is, you know, cool. We're doing an experiment that the Earth has never thought to do before. So here's my favorite way of looking at what the CO2 concentrations in the atmosphere might have been over the last 60 or 70 million years. So this is based on some oxygen isotope data from deep sea, and I've just done one transformation of this to make it, and it's sort of reasonable. We published on this about 15 years ago, but nobody really followed up on that. Here's CO2 and ppm. This is where we've been over the last 2 million years. So humanoids have been on the Earth for about 2 million years. This is where the CO2 range has been. So we're now at 400 ppm. So we're actually 100 ppm above where the CO2 concentration has ever been since humans first evolved. So we're now testing out pre-human conditions on the Earth. And it hasn't been that high actually since at least 10 or 12 million years ago, probably. If we get up to the 600-700 range, then we're talking about going back to about 40 million years ago. And the significance of that is it wasn't until the CO2 concentration in the atmosphere dropped below about 600 ppm that the Antarctic ice sheets formed. So the Antarctic was ice-free when the CO2 concentration was above 600 ppm. So it's just really an incredible experiment. If we get up in this range, we're talking about, you know, times when the Earth was much, much, much warmer, There was nothing resembling a human on the Earth back then. So it's true that the Earth has had high CO2 concentrations in the past. It just hasn't had high CO2 concentrations in humans at the same time. Okay, so finally, I got two slides here to think about this as a geologist, as a geological engineer, really. So you hear a lot about how fast carbon gets transferred between lots of places, like the atmosphere and the oceans, the terrestrial biosphere and the atmosphere and soils. But when things are transferred very rapidly on a decadal time scale, and you're worried about what's going to happen in the next few hundred years, you don't have to worry about those transfers. You just assume that all that stuff represents one reservoir. That's the way a geochemist looks at it. So if you draw a box around the atmosphere, the terrestrial biosphere, soils, the surface ocean, that's kind of a single unit. And it's about 3,700, maybe 4,000 gigatons of carbon. Now, normally what the Earth does to that box is it adds in a little bit of carbon every year through volcanoes and other kinds of emissions around the globe, and that rate is about 0.2 of a gigaton carbon per year, and that's typically almost exactly balanced by carbonate sedimentation on the ocean, which is about 0.2 of a gigaton carbon per year, and that stuff goes down to the ocean, and actually the Earth has a way of recycling that back into volcanoes at deep levels. So that's the number. It's 0.2 gigatons carbon per year, and it's a pretty small number. So here's a diagram I made up, and I put it on a log scale, and it's a little bit washed out. So this is carbon transfer rate. So again, we're not worried about the trees. We're just talking about carbon that's been in geologic storage as limestone, coal, oil, gas, and then transferred into the atmosphere. That's what the Earth does really slowly. And this is year, this is the transfer rate. We're now up at 10 gigatons carbon per year. The total geologic rate is about 0.2. If you just look at metamorphism, which is a particular way of releasing CO2 from rocks, it's about a fourth of that, something like that. So we passed the Earth's normal rates in the late 1800s, and we're now on the order of 50 to 100 times larger than that. So this is one way of saying there is no argument about the effect of anthropogenic carbon. It basically, all of the transfer that's happening right now is anthropogenic. Virtually nothing is normal. And I think one thing that's kind of interesting and maybe cute is that just the production of cement now produces about 5 or 6, 7 times more carbon per year than all of the metamorphism happening in all the mountain ranges around the world. So humans have gotten better at doing earth processes like metamorphism by a huge factor than the Earth has never been able to do that well. So we're way beyond talking about natural or normal processes here. There's nothing normal about this. You can argue about whether the temperature goes up and down normally. This is not normal. This has never happened. Okay, so this is what it looks like now. So right now we're taking 10 gigatons carbon per year. We're taking it out of geologic reservoirs. We're dumping it into the atmosphere. It gets redistributed in this box really quickly. About half of it stays in the atmosphere. Some of it goes into the ocean, and the only leakage is back down to the deep ocean, and that's estimated at about 2 gigatons carbon per year. So right now we're dumping in 10. We can expect the natural system to lose 2. And so that's a net of 8, and that's a big number. What we need to do is to get our first objective is to get this arrow to be the same order of magnitude as that arrow. That's step 1. If we can get to that, then we're no longer accumulating too much in the atmosphere system. All right, so here's the way I look at this. This is the carbon. So instead of looking at total emissions, let's look at how much carbon's released per unit energy produced, and this is primary energy. And this is carbon intensity in units that I made up of megatons of carbon per petawatt hour. Rob Socolow doesn't like these energy units, but it comes out to a nice number. So coal is, relatively bad. It's about 100. Exactly what you get out of that depends on how efficient your coal power plant is. Petroleum's down here at a number around 70. Natural gas is in here at about 50. And then if you look at some of the other things you can do, nuclear, renewables, coal with carbon capture and storage, or natural gas with carbon capture and storage, they're down here in this range of about 0 to 10 in these units. And what I've plotted here is what the world was doing overall for the last 200 years. And back here, mostly burning biomass, and then coal started to come in later. So all these numbers are high. And then gradually through the 20th century, this number came down close to 60. Now, that's the total carbon, including the biomass carbon, but if you just look at the geologic carbon, it ramped up from about 0 to somewhere up in here, and this is coal coming in and replacing just biomass burning, or being added to biomass burning. And then it's kind of fluctuated. It probably peaked in about I don't know what that number is, 1950 or 60, and it started going down. It started heading in the right direction. So this is the bad part here. It started going in the wrong direction in 2000. This is where we need to be. So if you want to, solve this problem, you've got to get down around 5, and over the next 150 years. So this is where we want to be. We'd like to go on a trajectory like that. That represents decreasing this intensity number by about 5 units every decade. Okay? So this would get you to where you want to go. So what would that get you? That would mean that if you were up at 800 petawatt hours production, which is about double what it is today, and you were doing it at 5 megatons carbon per petawatt hour, you'd still be putting out 6 gigatons of carbon per year, but that's not too far from the 2 that the oceans can handle. Okay, so the other thing that's happened recently is, of course, with the Chinese and the Indians making coal-fired power plants, they've gone off in this direction, and China's now agreed that, maybe they'll hit their peak in 2030. So they've added this little wrinkle to what we might have been able to do if we were on this trajectory. And that little wrinkle adds an extra 1,000 gigatons of carbon. So that's too bad, But it just means that we're going to go to try even harder after we get past that 2030 hump. And so here's an example. If you do CCS, you can't retrofit every power plant immediately, but if you started now and you did 1% a year for 100 years, you could ramp down the carbon coming from electricity production by coal and natural gas over this period, and you'd get yourself down in the range that you wanted to go. And if you added in more nuclear and renewables at the same time, it's possible you could make it. So people are doing CO2 EOR, and Jen talked about this a little bit. So fundamentally what that does is, because when they pump the CO2 down and they produce it again with the oil, they separate out the CO2 so they can reuse it, but they lose about 1/3 of it to 1/2 of it on every cycle. So they're kind of sequestering some CO2 while they do it. And so the way that they're thinking about this is, if you're using anthropogenic CO2 to do the process, you're doing a little bit of sequestration and canceling out CO2 that you'll get from burning the oil. So this makes the oil green. It could decrease the amount of CO2 per unit of oil burned by about 40%. So, maybe that could help a little bit in the meantime. In the long run, if you can get the biofuels and advanced artificial photosynthesis to work, you could get down there too. So I think all these things are the right things to be doing, and there are other things to do as well. Add in more wind and solar, of course. Okay, so carbon capture and storage. This is the cartoon I like to use for this. I agree with the other speakers who've talked this morning. I don't think we're going to get through the next 100 years without and have anything like a level of CO2 in the atmosphere that we can stand without carbon capture and storage. I think we're well on the way here, and there's a lot going on to pave the way, the rest of the way. So the DOE has had a carbon storage program going since the mid-90s. It actually grew during the Bush administration. And recently, in the last 5 years, the DOE's Office of Science, which is different from the Fossil Energy Office, is now putting some money into basic research related to carbon storage. And there's 3 different Energy Frontier Research Centers, and I'm actually the director of one of them. And we're looking at different aspects of this problem, like, you know, if you pump CO2 underground, the idea is that it flushes an area and then eventually gets trapped by a low permeability layer, but a lot of it gets trapped by capillary action because CO2 is a non-wetting phase, and how much gets trapped by that mechanism determines how much you can get in a particular formation. So we're looking at whether that trapping process works effectively. Could anything change due to chemical reactions? Is it permanent? We're actually looking at if you start making extra fractures or cracks in the sealing formations, whether geochemistry can help seal those, or whether it's a big problem in any case, and how much of it can actually be mineralized. If we're going to mineralize CO2, I think the best way to do it is in geologic formations underground and not by grinding up rocks at the surface. Some of the things that we're doing is improving ways of looking at rocks so we can understand what's going on in the subsurface, and also better computational methods. And one of the things that the DOE has to take advantage of is the national laboratories and the facilities that they've built at those laboratories. And this is just the Lawrence Berkeley lab. By the way, I work at Lawrence Berkeley lab, which is not Livermore. Livermore, your nuclear weapons are designed at Livermore. Berkeley doesn't do any of that stuff. We just do energy and basic science. So we have synchrotron, computational facilities, a new solar energy research center, a nanoscience center, bioenergy, and so on. Okay, so here's, how much time do I have? I don't know how fast. Okay, I'll just go through this quickly. So the Fossil Energy Office of DOE is trying to figure out, can we summarize what we need to know to decrease risks related to carbon storage underground, and can we produce some tools to analyze those risks so that anybody who's interested in this, either if they want to store it or if they want to regulate it, like the EPA, they can use these tools to evaluate risks relatively quickly. So we've had this program going for about 4 years now, and we expect to expand it and continue it. It's 5 or 6 national labs working on it. There's another group working on using advanced computation to shorten the number of demonstration steps that's necessary to get a carbon capture system added on to a power plant quicker. So, you know, there are lots of aspects of this problem that we're trying to work on, and people are making some progress. So this carbon capture simulation initiative is about to roll out its tools this year, and the National Risk Assessment Program, which is working on the subsurface storage risks, has been working on their tools, and they're finishing up a first set this year. And for instance, the EPA is very interested in what NRAP is doing, because they have to ultimately write the regulations for CO2 disposal wells, and if they write them to be too restrictive or expensive, like you have to monitor them for 100 years or something like that, it's going to discourage people from doing it. So there's feedback here between the DOE and the regulating agencies. I'm going to skip the details on this. Yet we're worried about induced seismicity. Everybody's worried about induced seismicity right now. It doesn't matter whether you're doing a geothermal project, you're doing fracking, or you're expecting to do CO2. You know, it has caught people's attention that Oklahoma is now the most seismically active state in the union. Okay, so a little bit on capture, and Jen talked about this already, so I'm not going to spend a lot of time on it. Of course, you have 2 choices. One is you can capture the gases at the source, or you can do something like photosynthesis, which is just going to take the CO2 out of the air and selectively use it. And both things can work. So one thing, this is a too busy slide, but one of the EFRCs that the DOE supports is on carbon capture. It's at Berkeley. Jeff Long runs it now. And they're working on using metal organic frameworks as a basis for doing CO2 capture. And they've come up with something really neat recently. So what they do is they use these metal organic framework, which are really high porosity structures, and they hang things like amine groups on the insides here. And what that allows you to do is to have a very porous structure for the CO2 can get in and out quickly, and you can have the chemistry going on these functional groups that are hung off the MOF structure. And what they've discovered is they can make a MOF work something like this. Normally for an adsorber, this would be an absorption isotherm. At a low temperature, it absorbs, it takes up a lot as you increase the pressure, and then to get it back off, you have to heat it up to a high temperature, and it usually is associated with a higher pressure. And so the amount of the adsorption sites that you can actually use is a small fraction of what you have available. What they've done is they've created a situation where they actually have chemical reactions going on with the amine groups in the thing, and it actually is a phase change adsorbent. And in this case, you can go from fully absorbed to fully desorbed over a relatively small temperature range. I mean, if they could get something like this to work, this would be really cool and would be a big advance. They just published this in Nature this year. The Joint Bioenergy Institute's going at biofuels in a particular way. There's 3 different of these bioenergy institutes. The one at Berkeley is led by Jay Kiesling, and their approach to this is to fix the plants, make the plants optimal for making biofuel. So increase the C6 to C5 ratio, lower the lignin content to the point where the plant will still stand up, but you don't have to deal with so much lignin. And then there's the issues of how to extract that from the plant. The lignin is kind of a waste product, and they're figuring out ways to make lignin valuable. And then they're trying to design microbes that will convert the sugars directly to fuels that you can use, like as jet fuel. They're going about this very systematically. It's a bioengineering project, and they've got $25 million a year, and I think they're using it pretty effectively. And their objective is to get biofuel costs right down to where gasoline costs are now. And they've made a lot of progress. They have a long way to go, but we're trying to get this to happen in the next couple of decades. It could happen. So they're doing a higher risk approach than some other people are doing, but they think they're going to get farther by doing it that way. Okay, so the other thing that's going on that's fairly big was just announced that it was renewed recently is the Joint Center for Artificial Photosynthesis. Some of you are familiar with this. There are different ways to try to do this. They're focused on making an integrated system that will kind of act like a leaf, but instead of making biomass, make fuel. They've been in business now for almost 5 years. They have made some progress. They were focused mainly on hydrogen generation from water, and they can do that very efficiently now, and they can make integrated systems that do it. This is the new building that we put up at Berkeley. It just opened last week to house this center. And what they're going to do in the next stage is work on CO2 reduction. This is much more difficult to do, and this is what the DOE has told them they want them to focus on. But other parts of DOE have suggested that they will help to support continuing work on the hydrogen generation part. So again, there's a fair amount of resources going into this, a lot of smart people. There's a lot of smart people here working on this too and elsewhere. They may get this to work at some point in the not too distant future. And even if it's 10 or 15 years from now, that's fine. That's going to be in time. And this just shows that they're doing all parts of the project, from basic electrocatalysis and other kinds of catalysis, but they're trying to build systems. And the point here is that sometimes you can have a piece of the system demonstrated in the laboratory to work, but when you try to actually make an operating device with it, you run into a lot of other problems you could imagine. And they're trying to get all of that to work together and get feedback happening in that loop. Okay, so one other kind of idea that's out there for utilization of CO2 is to use it as a working fluid in geothermal systems. And of course, if you're interested in using CO2 to react with ultramafic rocks, Peter Kellerman's latest idea is you make a geothermal system in an ultramafic body and you circulate CO2 through it, you extract the heat and hope that some of the CO2 reacts with the rock. So anyway, there's some of this going on. There's not a big focus on this, but the geothermal program in DOE has come back to life in the last 5 years, and they're trying to, they're really hoping that they can get geothermal to, you know, produce a lot more energy than it has up until now. Okay, so these are some of the conclusions, which I don't necessarily have to read. I do believe this first thing is true, and other people have supported this. Using CO2 in large enough quantities is a real difficult thing to do unless you're going to make fuel from it or use it to produce oil. Some of these other things have a ways to go. So, and that was what I was going to talk about. This picture I like to show because there's 3 reasons. One is this is the kind of thing we want to preserve, although I don't think this glacier is melting that fast. But also, it's the glacier that they're using to reconstruct CO2 and methane concentrations in the Earth's atmosphere over the last 100,000 years. And also, the guy who runs this project is Jeff Severinghouse, who just got elected to the National Academy this year. Thank you.
Time for some questions.
Thanks, great talk. I want to go back to one of your earlier points about you sort of dismissed the terrestrial carbon sink and carbon cycle implications. And I want to, I guess, challenge you a little bit on that. So roughly 1/3 of the net radiative forcing we have today comes from carbon, as you just demonstrated, from the terrestrial biosphere that's now up in the atmosphere. About 15% of the carbon that's getting put up is coming from land use change. And there's a large hysteresis, so the sort of grows back. The time frames of that growing back is non-trivial. So that if you put it up in the atmosphere today, you don't get it back tomorrow, you don't get it back in a decade, and you don't historically get it back in 3 decades. So I do think that there's an important point here is that managing that carbon is one quick way of not getting further on your curve. The second question or point would be the most recent IEA data suggests that in fact your projections going forward may not be true, in part because coal use in China they're working on it, and the most recent is that that fossil fuel emissions in 2014 were flat relative to 2013. So any comments on those 2 things? Thanks.
So in your water splitting chart, your diagram with the straight line, there was an arrow pointing to methanol or better, and I was wondering what that was. Was that a new method of generation instead of water, or was that a product that you are saying that it's going to be made?
Yeah, I think what they're referring to there is methanol will be the simplest thing because it's the fewest carbon-hydrogen bonds they would have to produce. If they can produce something that's got 2 carbons in it, that would be great, but they're trying to get at least to methanol.